engineer and doing anything at a time. A lot of stuff is that.
Oh, I liked it. I had a student teacher, so that's why I'm glad I'm out of it. Learning from them was hard.
Before we start, what's the line in the game? The Auburn LSU game. What is the Auburn plus what? Is it plus 3 or 7?
7.
Is it plus 7?
If we have the answer right, does that mean we can answer this?
Don't worry. I will do your quiz no matter what.
Oh, I wanted the A. I don't want the quiz.
Anyway, I'm going to go through 2 things with you. What?
10 and a half.
Is it 10 and a half?
10 and a half.
All right. There's a reason I was saying. I was just at some meetings with some of the board of trustees. We were discussing. Nobody really knew at that time. That's good to know. However, it is LSU. All right. Now, getting back to where I'm going, here's the idea. I'm going to take you through a block diagram. First, a depiction of a transfer function, a general transfer function described as a polynomial in the numerator and denominator. And then we're going to realize that first with block diagrams, small block diagrams, then with actual components with things called operational amplifiers. All right? So pay attention. This is real useful. This is something that in time you'll see a direct application for building active crossover networks like I talked to you about bows and speakers. So this is something that you can enjoy later if you choose. First of all, I'm going to say if you have any transfer function h of s, that can be rendered as some, and I'm going to choose it this way. Yeah, I'm trying to keep with the book's notation. After this, I'm going to break out. So it's going to be B0S cubed plus B1S squared plus B2S. And it's over some, call it S squared, or S cubed, pardon me, S cubed plus A1S squared plus A2S plus A3. I'll tell you why I'm doing it this way. This mirrors the book, but let me explain something to you. We could keep going on and put an infinite number of terms here, and this could be S to the n. Follow me? And you could have B0 there. Everybody understands? I could represent that with an infinite series. I choose not to do it because the logical extension is obvious. Does everybody follow me in this class? So now I'm going to show you how we're going to actually realize this. First way, this is one way. There are many ways. One way to do it is divide everything through by the highest power on S. You all see it's S to the third on this one? Now, I'm assuming it's going to be either a strictly proper or proper fraction. In other words, the power on S here will always be equal to or greater than the highest power on S here. Follow me? All right, now we're going to divide top and bottom. Oh, and one other thing. The coefficient of the highest power on S here will be 1. So if this was like 2, you divide top and bottom by 2 first to make sure that highest power on S in the numerator or denominator is 1. Do you follow me in this class? Now I'm going to go ahead and divide top and bottom by S. And what do I get? I get B0 plus B1, and it's going to be over S, plus B2 right here over S squared. And that's going to be divided by the quantity, and I on purpose did it this way, 1 over, and it would be simply 1 plus A1 over S plus A2 over S squared plus A3 over S cubed. Are you all with me on this class? Oh, I'm sorry, that should be getting Y'all agree with that? On purpose, I broke this one out. I didn't put it just one, I got one over that separate. With me? Now, what I'm gonna do is also bring it to mind that when we did this last time, do y'all remember how I had a function a of s here, any function at all, and it came out this way, and I brought back a portion of that signal, and here, and this is positive x of s, this is y of s. I didn't have time to finish this, but y'all remember that I showed you, maybe we'll finish this one right now. What we're going to do is get this, we're going to find out what y of s over x of s is for this one. It's called the transfer function h of s of the network. Are y'all familiar with the term transfer function? How many are? How many are familiar with the term output to input ratio? It's usually called a transfer function. How many are familiar with that? You should be, right? It's a ratio of output to input. Usually the symbol is h of s. Now, it'll be h of j omega in your circuits books, I think. Do you remember this class? How many do here? Back in the circuits? Y'all had circuits, right? Y'all remember output to input relationships? Those are called transfer functions or h of s. They transfer the input times the transfer function is the output. That's what it is. It's a ratio of y of s over x of s. Y of s is the output. Let me go through this part one with you, and please be attentive here. So if I'm going to do this, take a look at this. What is the signal right here? Just look at it. Isn't it x of s minus y of s? Y'all agree with that? Let me do something. Let me make this b of s here. Sorry. And this is the flow of the signal. So this is going to be, right at this point here, it would be x of s minus b of s times y of s. That's right here at this point. Do you all agree with that, class? I don't want to move too quickly, but I showed it last time. Do you all remember that? Now that is going to be multiplied by a of s to get y of s, right? I'll do this on the far board. So I have a of s. How about I just drop this s arguments? We know it's a of s, okay? Just drop it. So I have a times the quantity, and then it's going to be what? X, right? Plus, and it's b times y here is equal to y. Do we all agree with that?
Would it be minus dy?
You're so right. That's a minus. I apologize. Thank you. Take a look. Y'all agree with that? Make sure you do. Does everybody see it? Now let's go ahead. We want to get y on its own side. So first, if we multiply through, we have a times x here, right? Minus a b times y is equal to y. Agree? Nothing more than multiplying through. Right? Now what we're going to do is take the a, b, y on the other side, so we have y times the quantity, 1 plus a, b here on this side, and that's equal to a, x on this side. Just rearranging terms. Y'all agree with that? So what's the ratio of y over x? Y over x, or output over input, or the transfer function, which technically is h of s, is really equal to a, I'm going to put the a-s in there, over 1 plus a-s times b of s. And that's the relationship. That's the transfer function for that network. Yes, miss?
Why are there bars above X and under?
Just to make it capitals.
Oh,
No other reason.
okay.
You don't need them. Don't need them. Do y'all see what I've done here? Are you with me? Now I'm going to show you what I'm going to do next. I'm going to say if the forward amplification here is just 1, I'm going to put a 1 in here. Then this term simply becomes 1 here. And this simply becomes B of S. Y'all agree with me there?
Can you repeat that? Really quick.
Only thing I did was I made the forward gain A equal to 1. So anywhere there was an A here, I put 1. Are you with me?
Can you explain why you did that?
Yeah. Because now it fits the form right here perfectly. You follow that? I have 1 over 1 plus whatever that A1 over S plus A2 over S squared plus A3 over S cubed is, that's B of S. Do you all follow me on this, guys? It fits perfectly, doesn't it? So now what I'm going to do is realize this function. This function right here, or this H of S. Now the truth of the matter is, I use this to show you this H of S, maybe you call it H2. This is really H2 here. That's my H2. It's the second. Follow me? You all see this? This is one method of realizing a circuit. There's two that he talks about, and they are identical. It's just the way you go about where you put the first or second transfer function. This one I'm going to call H1 of S right here. Everybody okay with that? Now I'm going to realize the first one, H1 of S. And again, we're going to use the block diagram notation. Everybody with me? Be attentive. This is really important. So let me erase this. By the way, one other thing I'm going to mention. I just looked today. I have messages in my email, baginme@outlook.com. I don't use outlook.com. I don't know how you get that email. It's at auburn.edu. I don't know if that's stuck in Canvas somewhere or how you got that, but I have 3 or 4 emails that went to Outlook.
So your link to the OneNote was sent through your Outlook one, was what it was.
And so you're using that. Well, I apologize. I mean, I didn't know it was sent that way, but it should be at auburn.edu. My bad. I didn't realize. I thought the link was set. I guess I should have looked. All right, class. So if you want to contact me, baginme@auburn.edu, not outlook.com. It is associated with my name. That's where my junk mail. If I talk to a car dealer, he gets it. Anyway. You'll know what I'm talking about when you try to go looking for a new car. Never give them your phone number, your real email. You regret it for your life. So, now I gotta realize this. I'm gonna give myself some blood. I want to realize this right here. Understand? That's the original function. So I'm going to start with H1 of S. Now watch the way I do it. I start and say, well, here's my X of S. That's the input. It has to be times H1 of S to get an output. Follow me? H1 is like a block, right? So now it's going to be X of S. Well, the first thing I'm going to have is B0. It's just a constant B0. It's going to come out. Now I have to have B1 over S. So I come this way, and I'm going to have a block that says it's 1 over S here. And then coming out of that, I'm going to have a weight of B1 here. And I'm going to have a summer here, summation circuit. You'll see how I realize that. And then I'm going to have another 1 over S here. And then there'll be a B2 here. And it will sum here, and go here, where all these are summed together. Now please take a look at this. It's a strict, simple block diagram. Each one of those things has only one functional form. It's either a multiplier by a B or a multiplier by a 1 over S. And you'll see an op-amp will give you a 1 over S perfect. Is everybody with me on this class? You all see how straightforward this is? Now we just realized H1 there. This whole thing would be H1 of S. You all see that, class? Right? Now we we go to the next part. Remember, the forward gain on this one is 1, isn't it? Remember, the general form, and I'll put it here, was if you have a block that has a forward gain of A, and this is going to be your X here of S, plus here, summation sign, and this is a reverse gain of beta. This is Y of S, then Y of S over X of S is H of S, and that we want to set equal to this right here. Are you with me? Everybody with me? So by inspection, if we're trying to equate H2 here, H2 of S to that, to this right here, which is going to be A over 1 plus AB. Does everybody see what I'm doing here? How many do? Y'all see it? This is what? This is what we just figured out the input-output relationship of this circuitry is, right? We're going to make A 1, right? Because there's a 1 there. Understand? So I'm going to make it 1. And that means B for that circuit is what? Isn't it just A1 over S plus A2 over S squared plus A3 over S cubed? Please take a look at that. Guys, do y'all agree with that? You're just seeing what's left past the 1, right? Set it's equal to B, right? A is 1. Does everybody see that? Now, how am I going to realize that? Well, will you let me erase this right here, guys?
Yeah, can you tell me really quickly how you got that B A1 over S?
B1.
Like all that equation for B, really quickly?
This one?
Yeah.
It's just right here.
You just-
Take a look
you
here.
just took it out.
See how this is B? 1 plus. 1 plus whatever's there is B. Got it? Now we're going to realize this circuit using this block diagram. Well, this is where this thing's coming out right here. Can I erase this to give myself some room? Are you all okay with that, everyone? Because really what I want is that over there, right? I've got B here, that's what I want. So now what I do is this. I go ahead and I say what I need here is a simple summer, right? Where this is going to be negative, this is positive, correct? My forward gain is just 1, my forward gain. So I just took my reverse gain is all that. It's going to be A1 over S plus A2 over S squared plus A3 over S cubed. And all that's being fed back here in a negative. That's a negative sign. Isn't it, class? Are you with me? So follow me how I do it. I take the output, right? And I have to multiply it by A1S. So first thing I take the output, this is Y of S now. This is the complete output. And I put a block that has 1 over S here. And then I multiply it by A1. Then I have another 1 over S. So the effect of this is 1 over S squared by the time it goes through both of these. Do y'all see this? This is the flow of the signal. And then I have 1 over S squared A2. So now I have a block with A2 in it. And then I have another 1 over S. And I have a block with A3 in it. And now I take all these and they have to be added, but they have to be actually subtracted. The negative of them has. So there's going to be a negative sign here. And this would be a negative. And this would be a negative. It would be subtracted. But the summation means whatever these are going to be, it's either going to be it's going to be something where you're adding them. Some are added after they are negated, or there would be a negative sign. Are you with me? Y'all see this? Can I get a show of hands if you understand what I did and why I did it? You've got to go through this several times for it to burn into your brain. This is a simple realization method. It's called realization 1. The way you're dealing with this with polynomials, you realize the first polynomial, the top one, the numerator here, then you realize the denominator here. You still don't know how to realize the 1 over S and all that stuff, and you're going to get it in 1 second. Are you with me, class? Now, it doesn't matter if this is H1 of S and the remainder here, this whole thing is H2 of S. Do you think it should matter if we put H2 first and H1 next to each other? It makes no difference. So in other words, the other realization is putting this section first and then this section after. That's realization 2. It doesn't matter. They're effectively doing the same thing, same number of components. There's no advantage to do it either way in terms of block diagram. You don't minimize parts or anything like that. There may be an advantage in fabrication. That's the only thing I can tell you. And you don't know yet until you learn about fabrication of electronic components. That's later. So now we're going to realize this thing. But we're going to start by understanding operational amplifiers and how they realize simple things like 1 over S or A1 over S or any of these functions. Are you with me? So we're going to do it. But first, I have to introduce you to op-amps. Y'all got this down, class? That's the block diagram method to realize a transfer function, and it's important. Now, part 2. I'll get your questions. I'm trying to get through this because I need to. Problems I gave you last time were a little harder, but they have solutions and answers. All you have to do is just sit down and work. All right, now we're going to get through op-amps. How many people have had operational amplifiers? Did you not get them in your labs? Not yet, huh? All right. Well, start a new section. You're about to learn about operational amplifiers, and this little component here is a lifesaver. Anybody I know is an electrical engineer, for God's sake. If you didn't have this, you'd have to build it from scratch with transistors, and it's a pain in the butt. Here's what an operational amplifier does, and this is the ideal operational amplifier. By the way, are you still uploading those videos, right? Is there
Yeah, I got behind on a few of them.
What?
I'm behind on a few of them, but I'm starting to do it live now.
How many have seen his videos? All right, I encourage you to look at them. If you have any questions about the lecture material, send me the link again. I'll send it out to everybody. Okay, so I'll post it on OneNote. I think
It's already on OneNote.
It is on OneNote?
Yeah.
Yeah.
All right, I encourage you to do that because a lot of times the second time through, anything that's difficult, bells will ring. It'll make sense. Back to this with an operational amplifier. It's symbolized by a triangle. There are 2 terminals. There's a negative and there's a positive terminal. The negative is called the inverting, the positive, the non-inverting. That's not important. Then there's an out. Now, this essentially is the operational amplifier. What it represents is thousands and thousands of transistors that do what I'm about to tell you. And they force this to happen because they have an active power supply outside that's never shown. Sometimes you'll see like this, plus 15 volts. It makes no difference. It's just saying the power supply is 15 volts that you use. All that you don't worry about. What you worry about for an ideal operational amplifier is this. And that's the way most designs are done that I've done. You start with an ideal operational amplifier. The actual one has slight differences. It's a bias offset you have to work with, but this is very, very close to everything you need to know. What an operational amplifier does is this. It allows no voltage difference between these 2 terminals. So effectively, if that's V1, this is V1. Got it? No matter what you do, there will never be a voltage difference between those 2 terminals. And if there is, the op-amp will go into saturation and the whole circuit behavior falls apart. The second thing is there is no current. This would be I minus, and this would be I plus. There is no current. I minus equals I plus equals 0, and V1 equals V1, excuse me, I should say V minus equals V plus equals V1. There's no voltage difference. Now, no voltage difference, no current into it. The way that's done is electronically. There's all sorts of feedback networks that force this to be the case. Remember that. It's not something that's natural. It's not a passive circuit. You could never do this with just passive components. So let me show you the first circuit for operational amplifiers that we do. We start by saying, if you have some impedance, and I'm going to call it Z1 here. Z1 could be anything. and you plug that into the negative terminal of the operational amplifier, and take the positive terminal and ground it. Here is going to be the input voltage, and I'm going to use plus the minus V in here. Then this is the output, but between the input negative terminal and the output, you're going to have some Z2. That's any impedance, and it can be in the S domain. It usually is in the S domain. And then you're going to have an output here, so that's connected. The output voltage, V out plus to ground, is right there. Now, usually in the book, they will never show the ground terminals, here and here. They'll show this ground, but everything else is not shown. They assume V0 plus here would be measured with respect to ground. They assume Vn would be measured with respect to ground. That's an assumption. Now, we're going to apply the laws I just told. I said there's no voltage difference across those terminals and no current into the terminals, right? So watch this. When I talk about a voltage with a ground potential, what do you assign that voltage? 0 volts. So there's 0 volts here, right? How many volts at the negative terminal? If it's 0 here, what is it here?
0.
Has to be 0. Remember, whatever's on the positive is on the negative, whatever's on the negative on the positive. Now that said, how much current is going this way? Vn divided, or Vn minus 0 over Z1, isn't it? The voltage difference across the first impedance, right, divided by the impedance. So that's simply Vn divided by Z1 is I1. Do you all agree with this? Yeah. Everybody with me? It's straightforward. If Vn's on one side and 0's on the other, the voltage difference is Vn. Divided by impedance, you have current. It's that easy. Now, that current must flow. It's a reality. I1 will flow if this is a voltage, something other than 0. If it flows, how much of that current can go into the negative terminal? None. All of it flows this way, doesn't it? So therefore, I1 flows here. Now, what's the voltage across Z2? I1 times Z2, right? Or I can say now it's I1 Z2, but since I1 is Vn over Z1, I can say this voltage, and let me label it plainly, is simply I1, which is Vn times Z2 over Z1. You all see that would be the plus to minus voltage across there, right? Because the input current is Vn over Z1. Isn't it, class? Take a careful look. Convince yourself. It's not deep. This doesn't require a lot of deep thought. It's not looking 10 moves out of a chess game. It's something very simple. Now, if you see that, what is the voltage between the plus and minus terminal here? And I want to make sure I show you this, because kids make this mistake routinely, and I think it's because they're not careful. The way I always tell kids, anybody, any student, undergraduate, graduate, high school, doesn't matter. If you want the voltage between 2 points, you start at the negative terminal, and you go around. So I'm going to go from here to this point, still 0 volts. From here to here, it's still 0 volts. And then I get a plus to minus voltage drop, or minus this voltage, isn't it? And then I'm back at the positive terminal. So I can say V out here would be minus Vn times Z2 over Z1. And therefore the transfer function, the relationship between output and input, V out plus over Vn, is equal to H. The transfer function is a function of S, in this case just H, it's not a function of S, is simply going to be minus Z2 over Z1. And it's that simple. Are you with me, class? That's the general transfer function for a circuit that looks like this. Agree? Now I'm going to show you ways of implementing any constant and any 1 over S term based on operational amplifiers. These are actual devices. You can go get chips that have maybe 10 operational amplifiers, and you can use them to your heart's delight to do this stuff. So over here, this is analog computing. It's not a digital computer. Jeff, when you were in school, didn't you have to do the analog breadboarding of computers? I did too. What it was, the first computers were done with effectively operational amplifiers and just wires. We literally, put capacitors, resistors, and we plug away at these breadboards. There were giant ones like this, and we build operational amplifiers, or we build circuits that were realized transfer functions, usually filters. That was for me back in the day. Do you remember doing that back in the day in here? He did his undergraduate in electrical engineering here. Well, no, you did it up there, not even at Brown Hall. You did it over at Dunstan, right? So he's pre-war. He's a long time ago. He's old like me. Getting back to this, now let me show you how to actually implement this stuff. I hope that's not there.
I don't pregame before the quiz.
I had a person do that one time.
I will not be that person, I promise.
I mean, I didn't want me. It's just if somebody sees it, I should have said something that bothers me. Anyway, back to this. Follow me on this. Now, if we want to implement one of these things, remember how there was a lot of constants A? Y'all remember that? And then there was 1 over S. Let me show you the 1 over S first. If you want to implement a 1 over S, you do it this way. You put some resistor R here, and then you simply put the operational amplifier here, ground it, and now you put a capacitor here to ground. It comes out. This is input, V in. This is V out. What's the impedance of a capacitor in the S domain? Assume no initial conditions and all the stuff we're doing. 1 over SC. So it's 1 over SC or CS. That's the impedance. Now we know that V out over V in, which is the transfer function of this one. Now this is the function of S. That's equal to minus that impedance divided by this impedance. So it's minus 1 over S times RC. Take a careful look at that. Do y'all agree with that? Output impedance, 1 over SC divided by impedance R. It's 1 over RC with a minus sign, correct? Because it's got to have a minus sign, right? Please make sure you see that is equal to this. For that circuit where you have a resistor between the input and the negative terminal, and the positive terminal is grounded, and then you have a capacitor between the negative terminal and the output. All right, you all see that, class? Now that's equal to this. That's not quite what we want. And you'll notice if you make R times C equal to 1, you simply get minus 1 over S, right? Do you agree with me? So you can choose any values for RC you want. Now the next thing I'm going to do is this. I'm going to say, I want to just take and get rid of that negative. So then I can do this. I can take this circuit and add it in series to the next circuit. And this is called an inverter. Write this down. It's this. You can just put R here, and now V out, but this is V in here, and this is grounded. For this circuit, V out over V in is equal to simply minus 1, and that's equal to the transfer function of this circuit. Y'all see if R's are the same, you get minus R over R, which is minus 1, right? So now if I put this circuit in series with this, don't I get a minus 1 over S and plus 1 over S? So I'll make the point, if I want just 1 over S, I can do this. I can take that circuit right there, and I can add to it this circuit. And now, my V out, let me get rid of this. And now for this circuit here, my V out over V in is equal to simply 1 over S. That's one way of obtaining that. Are you with me? And this is generally called an integrator. Now, I don't have time to go through why yet. But everybody with me on this one, class? The next one I'm going to show you, there's a lot. The next circuit I'm going to show you with operational amplifiers is a summing circuit. And this is very useful, so please write this down. I know you've just been introduced to operational amplifiers. I'll give you problems, and I'm only doing the simplest possible circuits. I don't want to cause you to have concerns about material overload. This is not that difficult. It's based on very simple principles.
Does the first R have to equal the last two Rs?
This R and this C multiplied together have to be 1, but this R has to equal that R. I can call R1, R1 if you want. Call that R0. Call it R0 there. All right? Are you with me? Now, the next thing we're going to do, can you see anything? I want to make sure, I don't want anybody that can't see what I'm doing. Now, the next thing I'm going to show you is something called a summer circuit. Or a summing. Just call it a sum circuit, really, like that. And for this one, I'm going to go ahead and take 3 inputs. You can have as many inputs as you want. Call that V1, V2, V3. I'm going to put 3 resistors in front, R, just all R. Put them together, like so. Then I'm going to take these and put them into the negative terminal of an op amp. I'm going to ground the positive terminal, and I'm going to put another R here, and I'm going to talk about my output here. And I'll show you how easy it is. Just write it down.
Those are all the same.
Are you ready? Now think about it. What's the voltage here?
0,
What's the voltage here?
0,
All right. How much current flows here on the first one? How much current flows in the second one?
V2 over R,
Third one?
V3 over R,
What's the total amount of current flowing here?
V1
This
over R.
plus this, and no current can flow into the negative terminal. Follow me? So the total amount of current here is really V1 plus V2 plus V3, right? Divided by R. That is the current I flowing this way, right here. Correct, class? All right, what's the voltage developed across this resistor? I'm going to put it plus to minus. Just think about it. It's that current times R, isn't it? What's the voltage? V1 plus V2 plus V3. You'll notice it's plus to minus. So the voltage here is just V1 plus V2 plus V3. But the sign is negative to positive, right? Everybody? Current times resistance is voltage. Current is V1 over R plus V2 over R plus V3 over R. Do you agree with that? Just multiply that by R, the R goes away, which is nice. Now, the output voltage is actually what, though? The negative of that, right? So the output voltage is the negative of that. So what are we going to do? This output voltage is just minus the quantity V1 plus V2 plus V3. What are we going to do? Put an inverter. Yeah, just do a simple inverter. Just put a resistor here, R, another R, then put it into a negative, positive, ground that one, take that out, and that's V out. And that's your V in, and V out is now equal to V1 plus V2 plus V3. And how many of you can see you could extend this to any number of input voltages? Can you all see that, class? And therefore, I can sum the circuits, right? And if you wanted to subtract one of these values, then you could put it through an inverter before you added to that, and it would subtract it. Do you see that, class? How many do? So now we have the basic building blocks to realize anything, any type of polynomials in S. We can build the circuitry that will do this. And in truth, you will see, because S itself has both a real and a J omega term, we can get a frequency, any frequency domain response we want now. We can do all sorts of stuff. We can build any kind of filter you want, and that comes a little later, but you have to see how its basic building blocks allow the fabrication. Do you all see this, class? And I've chose to use the realization 1 and 2 method. There are a host of ways to do it. Now, you got a quiz coming up, so I'm going to do this, and please be safe at the LSU game.